Okay, so we have done the geometry, we've done the mesh, and now we are going to actually run Fluent and calculate the heat transfer from a simple stationary disk in a free stream. So I'm going to do essentially these three, all of these three within Fluent. I don't particularly like the results in Workbench because I'm old fashioned that way. So I'm going to run Fluent and do all three of these in one video. First of all, we just double click on the setup icon and that opens essentially Fluent. I'm going to leave all the defaults here. I could do it in parallel. I have a quad core on my laptop, but I'm just going to do it series at the moment. So okay. So that runs Fluent. It's loading in now the mesh and all the defaults, and that's it. So we'll check the mesh. That's fine. Volume, I don't know what the volume is, but it's not negative, so that's okay. Just look at the scale, make sure it's right. Often mistakes can be made with the scaling. So I created it in millimeters, it already knows that. I'm looking at it in centimeters because I work in centimeters. So it goes from -60 upstream of the center of the disk to 120 downstream. So a little bit away from the inlet to prevent inlet issues. Further away from the outlet, so the wake doesn't interfere with the outlet, or vice versa. And then plus or minus 60 centimeters up and down, and the whole thing is 5 mil, 50 mil thick. So I'm not actually going to do anything, I'm just checking that what I did was correct. So we'll close that. So what we are going to do is just work our way down the left hand side and eventually run a calculation. The first thing, models. I'm going to do a laminar solution initially, because once you add turbulence it gets more complicated and you have to talk about the right turbulence modeling. I don't want to do that for this particular demonstration. What we do want is heat transfer, so we have to turn the energy equation on. So now it's on, so now we're solving for heat transfer temperature. Working our way down here, materials. Fluid default is air, solid default is aluminium. I'm going to stick with them. In reality, aluminium, the conductivity out of aluminium is way too high in reality. It should be about 30 or 40 for a brake disc. Grey cast iron is a common material which isn't in the database over here, so I'm just going to leave that. So in reality you would change not so much the density, but the specific heat and the conductivity to match the correct values for a typical brake disc, or for whatever you're doing. I'm not going to bother with that. No, just close. For the air, again, take the defaults. The one change I am going to make is that I'm going to have an incompressible ideal gas, and what that means is that the density changes with the temperature, but doesn't change with pressure. Change, create, close. Cell zones, we have a fluid zone, which is air. Just fine, I'm not going to do anything with that, just leave that. And we have a solid zone, which is our aluminium. Again, it should be changed to something more realistic. What we're going to have is, at the moment we've got no heat transfer anywhere. So either what we could do is click on fixed value and make the disk a constant temperature. That's not what I want to do. Or click on source value, and in the source terms here we can have a constant heat generation rate per volume within the disk, and that's what I'm going to model. So we've got no sources at the moment, so I'll edit. I'll add one source, and we'll make that heat generation rate a constant. So it's per meter cubed. So I'm going to make it 100,000. So that would be 100,000. That seems maybe a lot of watts, but it's per meter cubed, and actually the volume of our disk, I guess it's over here somewhere, is actually quite small. So the actual wattage being generated is not as large as what you might think. In fact, this number is probably too small. So click OK, and now we have 100,000 watts per meter cubed being generated within the disk. Boundary conditions. So we named various things as wall, so it knows it's a wall, knows it's a wall, knows it's a wall. Symmetry, it knows it's symmetry. Fortunately we spelled that wrong, so it doesn't know what it is, so we'll just put that as symmetry, and next time we remember how to spell symmetry correctly. Okay. We need some flow, so velocity inlet. I'm going to give it a low velocity, so 10 centimeters a second, which is crazy low really, because I want to keep things laminar for the moment. Thermal, I guess we could put that at some sort of typical air temperature. I'm just going to leave it at 300 for the moment. Okay. Velocity outlet, gauge pressure 0, thermal again, I would have that match in the inlet temperature, because what happens upstream is the same as what happens downstream. If we have any inflow because of recirculation, that's the temperature of the air that will be flowed in to the domain. Okay. Everything else is right. Okay. So there's actually no options on these. So wall bottom is the bottom wall, or fluid is the main side wall, this wall over here. Wall top is on the top wall. These walls here have been created automatically by Fluent. So these are our extra walls due to that interface between the disk and the fluid. We also have these as extra regions that were generated automatically by Fluent. There's nothing we can do with these are interfaces, so all there is a name. Wall 6 and wall 6 shadow are the ones we need to work with. So if we edit wall 6. So this, you see, has momentum options. So later on in a different video we might make this a moving wall, we might make it spin. Also it has thermal options. Be careful that you have the right material, we only have one, so that's fine. And this is a magic bit, it's now coupled. So if you didn't create these interfaces, which were unnamed, you wouldn't have these options here. This is a key to getting this conjugate heat transfer to work. So we want coupled. And we ignore all of this over here. That's okay. Thermal momentum. That was wall 6. Wall 6 shadow. No momentum options. So this is a disk if you like. Thermal option again, coupled in the right material name. We only have one material, so it's automatically correct. We'll ignore all this over here. Okay. So because of them two things, we now have a coupled solution between the fluid and the solid disk. I think everything else has been done. So we'll go all the way down, solution method. I'm going to leave the defaults for now. Seems common to change this one to one of these ones. So you need to go away and read a little bit more about what the best way to set up your solution method was for your particular problem. Solution controls, again, sometimes you can relax these controls to get a better convergence. Monitors, I'm going to go with the default. I'm not going to put a special monitor in the wake or anything. We need to initialize the solution. Just do the hybrid initialization. There we go, that worked. Check the case. Yep, no problems there. Stick in a big number. I'm going to say 200, 220, and calculate. So now obviously it's gone off and it's doing the calculation. So the solution is finished. It's done the 220 iterations I asked it, but it hasn't reached its convergence criteria. So this value here for continuity hasn't got below 10 to the minus 3. That's a white line. You see the white line is horizontal. So as far as the solution is concerned, it's converged, even though it hasn't met our criteria. That's either because the solution has truly converged, because it's fairly simple, or probably because our mesh is too rough. And we knew that when we did the mesh, we said it was a bit rough. It may well also be that the physics is such that it's finding it hard to converge the particular physics we're asking it to do. I suspect it's just the mesh. So I'm going to ignore that for now. In reality, I go back and look at that a bit more, maybe go back and redo the mesh, but I'm not going to worry about that at the moment. So okay, so I'm going to do the post-processing in Fluent. I prefer doing it in Fluent. So we're just going to continue our way down the left-hand side. So I'm going to go to graphics and animation. And we're going to look at contours, setup. So let's look at, just to check things are okay, velocity inlet, velocity outlet. and the symmetry planes. Let's display that. Oh, let's fill them. Let's get that wrong. So flow, left to right, disk obviously there, pressure drop across the field, as you would expect. Let's look at velocity. So we had wall boundary conditions on the top and bottom. Might be useful to change them to a pressure outlet or indeed symmetry to get rid of this boundary there. That might be a little bit of blockage going on there, maybe not. But you can see clearly zero velocity on the disk. It's not spinning or anything, it's just stationary. You can see our wake around the disk region. So we had quite a rough mesh around here, so maybe that's where you can see it's not. It should really be symmetric about the horizontal line there. The reason I didn't do a symmetry plane there is that once we spin the disk we would lose that. So I did the full domain, but really it should be symmetric about there. And the fact it's not suggests that either the Reynolds number is too high, but I don't think it is. It's about 10 to the 4 for laminar flow, or that the mesh is not good enough. And I think the mesh is just not good enough. You can zoom in a bit. If we click off node values and display, you get an idea of the mesh size, and you can see they're probably too big around here. So we go back and redo that mesh and maybe get better convergence. Do node values again. Heat transfer, let's stick some temperature on. Display that. So a hot disk, not particularly hot, 471. I don't think that's particularly hot for a brake disk. It's hot everywhere because we had heat generation across the whole volume. You might want to just have the heat generation in an annulus around the outside, so potentially we could go back and chop up the disk so we just had heat generation in where the pad was, but that's a refinement. Fluid 300, so that looks right. So fluid at 300, a hot disk, so then we have our hot wake behind here. So that's looking actually quite nice. What I'm going to do, I'm going to look at the boundary there. So I'm going to slice this essentially as we did when we were meshing down here and across here. Now when I did the geometry setup, 0, 0 was the center of the disk, so it's going to make slicing this up hopefully quite easy. So we'll go into here, new surface, plane, and because I know 0, 0 is in the middle, I'm just going to use these guys down here rather than aligning with any particular surface. So we'll do one at x is horizontal, so x equals 0 should be a vertical plane down here. So in fact, here we'll do that. So 0, 0, 0, make that another number. Plane 15, I'll just leave that as a default name and create. So over here we now got plane 15, let's just see if that worked. There we go. So now we have a vertical plane there. So I'm just going to look at that now. Display that should be X. And then zoom in. Oh, a bit more. A bit more. So because I suspect the Reynolds number is so low, it looks like we've got quite a thick boundary there. But just to check how I'm meshing, I'm going to draw the mesh on that. Then 15, display, close, display. So as you can see, the temperature change, I guess that's the edge of the disk there, to the fluid, that temperature boundary there is very thick. So the boundary layer mesh is easily capturing that change. So it's probably quite a good calculation of the heat transfer. If we had any more realistic, maybe Reynolds number, high velocity, as the Reynolds number increases, the boundary layer decreases. If we went turbulent, although that theoretically is a thicker boundary layer, because of the higher Reynolds number, it would be thin as well. We might have to refine our mesh there, but that looks actually quite good. So that's okay. So let's add another plane in the other direction. So in the, let's plot the whole thing. I don't know what we're looking at. So in the y equals 0, so y equals 0 across there. So 0, 0, 0, these can't be the same. 40, 99, 10, then 16. So there's 16. So now we have a plane in the middle. So So there's the temperature variation in the middle. Let's go to that mesh. And because it's kind of symmetric-ish, it looks kind of similar. There's our wake, and there's our temperature boundary condition. Fantastic. So that's it. For the moment, that's a very simple geometry that we've done there. There's the disk. It's not right. It's a very low velocity. We'll probably want to change that velocity to something more realistic. We want to get the disk to spin, or maybe do that in the next video. The disk is aluminium. That's probably not the right material. We want some grey cast iron or some other material property in there. The mesh isn't fantastic. We'll go back and redo the mesh. But essentially, by going through it in that very quick way, we've learned how to do conjugate heat transfer in Fluent. And there we will go back, probably all the way back to the meshing, and do all again, more refined, it would take a lot longer, put in the proper parameters, proper velocities, do mesh dependency studies, etc.